In your mechanics class, you learned that power was work divided by time. This was important when you were comparing things like two different motors, or maybe two different cars that were the same mass. They both start from rest, and they both accelerate up to the same freeway speed, but one of them can do it in a much shorter period of time than the other one. They both did the same amount of work. They got the car going from 0 to some final velocity. They both had the same change in kinetic energy. They both did the same amount of work, but one car could do it a lot faster than the other car. Maybe that's important to you. That's what power tells us, that it did the same amount of work in less time, so it is more powerful than the other car. In electronics, it just makes complete sense to use power instead of energy, because we're not just moving individual charges, they're flowing through the circuit. So we have charge per unit time. We have a current, charge per unit time, moving through our devices in our circuit. So if we were thinking in terms of energy, we'd always have this, well, how long is the light bulb on? And the light bulb's dissipating a certain amount of energy, but how long is it on? And time is always coming into play. But if we talk power, then we don't have to worry about that as much. So our light bulbs consume a certain amount of power. They dissipate a certain amount of energy in a given amount of time, or they have a power equivalent to a certain number of watts. A 60-watt light bulb, a 100-watt light bulb. And that tells us the energy they use per time. The power consumed by an electronic device is equal to the current times the voltage. But we know for our resistive devices that V is equal to IR. That means we can substitute using V equals IR into our equation for power equals IV and come up with a couple of other forms of that equation. Power is also equal to I squared R or V squared over R. And you just use the equation that makes the most sense for the information you're given in the problem. Let's look at an example using some light bulbs. You may be familiar with light bulbs that are rated by wattage. For many, many years, we had one type of light bulb, an incandescent light bulb. So rating them in terms of how much energy they use up in a given amount of time was okay because that was proportional to the light that they emitted. But they used up energy in other forms also. Those light bulbs would get hot. So they converted a lot of the energy into heat and a portion of it into light. But because we were comparing light bulbs that were all the same type, we could use power to indicate how bright they were. Then new light bulbs came out, compact fluorescent light bulbs, and now LED light bulbs. And those can produce the same amount of light and use much less energy, much less power is consumed by those devices to produce the same amount of light. So now we have to rate light bulbs not in terms of how much power they consume, but instead by the amount of light they produce. So you'll often see them rated in lumens. That's how much light they produce. And then it'll say, because we're so used to thinking in terms of incandescent bulbs and what a 60-watt light bulb is, or a 40-watt or a 100-watt, they'll often say this is equivalent to a 60-watt light bulb, but it only consumes 5 watts. Because our household current is set to operate at 120 volts, most light bulbs are rated at that voltage. If you hook up a light bulb to 120 volts, it will consume a certain amount of power. A 60-watt light bulb will consume 60 watts of power. Tricky things happen when we hook them up in other configurations when they're not getting 120 volts. So let's take a look at that. Let's say light bulb 1 here is a 60-watt light bulb, And light bulb 2 is a 100 watt light bulb. If we hook them up in series, like I show on the left, which one will be brighter? And how much power will each one dissipate? First, we need to find the resistance of each of these light bulbs. If we know that light bulb 1 is rated at 60 watts at 120 volts, and light bulb 2 is rated 100 watts at 120 volts, then we can figure out the resistance of the light bulbs. We have three different forms of our equation for power. Power equals IV, power equals I squared R, or power equals V squared over R. So which one do we want to use to figure out the resistance of these light bulbs? We're given the power, and we're given the voltage across the light bulb. So we want to use power equals V squared over R, and we can immediately solve for the resistance of each light bulb. $240 ohms for the resistance of light bulb 1, the 60 watt light bulb. 144 ohms for the resistance of light bulb 2, the 100 watt light bulb. Does that make sense? The one that dissipates more power when it's hooked up to 120 volts has the smaller resistance? Let's see. When both of them are hooked up to 120 volts, the voltage is the same for both of them. So the current drawn has to be greater for the one that's producing more power. That means it has to have a smaller resistance to get more current from the same voltage. So the bigger the current it draws with the same voltage, the more powerful it's going to be. Our 100 watt light bulb has to have a smaller resistor to get more power output. Now we know what the resistance is for each of these light bulbs. Let's hook them up in series. And let's just keep our 120 volt power supply. So how much current is flowing through this circuit? A little less than 1/3 of an amp. The current has to be the same through both of these light bulbs. So how much power are we going to get from each one? The one with the larger resistor, let's take a look at our equations for power again. They both have the same current. We want to know which one's going to be brighter, which one's going to dissipate more energy. The one with the bigger resistor is going to have more power output because they both have the same current flowing through them. So we can use I squared R to see how much power each one dissipates when they're hooked up in series. $23.4 watts. And that's for the 60 watt light bulb. A light bulb that dissipates 60 watts when it's hooked up to a 120 volt source. In this case, it's not seeing 120 volts because it's sharing that voltage with another light bulb in series with it. So it has to be producing less power in this case. And our 100 watt light bulb would only dissipate 14.1 watts in this configuration. That tells us that light bulb 1, the 60 watt light bulb, would be brighter than the 100-watt light bulb if it's hooked up in series with it. If they're hooked up in parallel, and we make our battery voltage 120 volts, well then each one is seeing 120 volts. Our 60-watt bulb will dissipate 60 watts of power. Our 100-watt bulb will dissipate 100 watts of power. And the 100-watt bulb will be brighter.